In this talk, I chose to do something that is more simple, just like a simple introduction to RAG, but also a deeper dive with methods on how to improve it, because I realize some of you have already played with RAGs, maybe you've even deployed them, but some of you have probably no knowledge at all. So I kind of wanted to have something for each and every one of you to learn from this. So about me, I'm a machine learning engineer at Zimmer Biomet, which is orthopedics medical devices company. I'm based in London, and we deploy AI models onto medical devices. So sometimes that's software, but sometimes that's robots, sometimes that's implants with smart sensors. So that's what I'm working on. Other than that, I'm also a member of DataKind UK, which is a charity that helps other charities use data science to improve their operations. And I really like Python conferences. I've been a participant and speaker at PyData London. Hi, John. And I've also spoke at EuroPython. This is my first PyCon Ireland talk, and I'm very excited to be here. So the tools we're going to use here are Jupyter Notebooks for running the code. It's just easy. You've probably all used it before. It's you get your answers back, and it's easy for experimenting. For the LLM framework, I've chosen Llama Index just because I haven't used it before. I think the first kind of tool that was popular was LangChain. There were some issues with it in the beginning in terms of the open source community, but now it's becoming much better, so that's a good alternative. And I've also heard good things about Haystack. For the vector database, and I'm going to explain later on what does a vector database mean, I've chosen FAIS, which stands for Facebook AI Similarity Search. It's an open source tool, just like Llama Index, for using a vector database. But some alternatives, which are good ones, are Qdrant, PyCon, and Chroma. For the actual LLM that we're going to be prompting and sending our queries to, we're going to use OpenAI. And this is, so the OpenAI API is obviously a paid service, so you're going to need an account and subscription, but it's not too expensive, so hopefully it won't be an issue. Alternatively, you can use Anthropic or Hugging Face. So if you're on a budget, Hugging Face is a good alternative. The data set that we're going to use in this use case is the UK General Elections 2024 manifestos. So for those of you who don't know, this year we had general elections in the UK, and this image was not generated by AI. These are real candidates for the Camden Council in the UK, and only one of them became Prime Minister. I'll let you guess who. So there are multiple parties. I've downloaded their manifestos. They all come in PDF format. And usually parsing is a pain with these kind of PDF documents. And that is because you have paragraphs and you have tables. And when you try to parse that into simple text, you lose the context. So for example, when you want the electricity generation, transformation, and storage to be in the same line as the 50 billion pounds, it will be sometimes hard to parse it in the same line. But I will show you tools and methods how to overcome this challenge. So everyone's talking about RAG, and specifically in this conference, I think I counted at least 5 talks about RAG. Luckily, I'm the first one, so everyone else will be copying from me. And there is a lot of hype around it, I agree. And is it too much hype? I think maybe, but I'll let you decide, because these tools are already developed and deployed into production in various settings. In the company I work for, we've already deployed it internally to be used in various teams across the world. And we're also going to deploy it for use by our patients soon. So it is something that is being deployed into production. So there is some in it. Maybe too much? I don't know. I'll let you decide. What is actually RAG? So with the rising popularity of LLMs and ChatGPT and OpenAI and all of their competitors, one of the most popular use cases on how you can actually use it in your products and tools is you can hook it up with your own internal database of documents that might not be exposed to the internet, and you cannot search for it in Google, for example. So you can hook up your internal documents database with an LLM, and you can talk to a chatbot about it, for example. You can query whatever queries you can think of in human language and just ask questions about your documents. Some of the use cases you can think of are in the medical world, for example, in something that we are working on right now. A patient can talk to an LLM about their condition. Let's say they are recovering from surgery and they have some kind of fear out of a symptom that they're experiencing, and they want to know whether it is common when they're in their kind of surgery and in their kind of like condition. But you can also think about other use cases. So you can think about in the legal world, it can create legal briefs from a collection of documents that are very specific to a very specific case. You can also think about how it can generate portfolio recommendation in finance, given a person's personal financial condition. In education, it can give curriculum recommendations for teachers based on the teacher's preferences and their class situation. So the possibilities are endless, as you can imagine. In our specific use case, the architecture is going to look like this. Obviously, this is a more simple version, but you can think of how it can become much more complex very quickly. So we will have a collection of documents. It can be PDFs or text in raw format. And then we are going to use Llama Index in an ingestion pipeline for making those documents ready for embeddings. So we're going to split them into smaller chunks. We are going to do some cleaning and maybe other kind of like pre-processing steps. Then we are going to feed it into an embedding model, which is provided by OpenAI in our case. Now, the embedding model, what this means or what this is going to do is it's going to create embeddings from our simple text, from our pure text. What does embeddings mean? For those of you who don't know, it is essentially creating a numerical representation of a text that a machine can read. So I recommend, if you don't know anything about it, search for a very simple model called Word2Vec and just read the paper. It's very easy to understand. It will be a good introduction into what embeddings actually mean. So for now, just think about it. This will take text and we'll create a vector of numbers for it for a machine to understand. So for all of these chunks of text, we are going to create embeddings and we're going to connect to them or hook them up with metadata. Sometimes it can be the file name, or sometimes it can be the name of the collection from which they come from, or a book, or whatever you can think of it, and then we can push all of that into a vector database. So a vector database is just a database that is optimized for storing vectors, but then also searching through those vectors. And in our case, as I mentioned, that we're going to use FICE by Meta. So then after we've done all that, a user comes up with a query to the chatbot, in our case, an LLM application, and that query is also embedded. So we're also going to create a numerical representation of that query. Once we have that numerical representation, we're going to try to find what are the closest documents or closest vectors that we have for that query, and we're going to send all of that back together with the query, so the relevant documents and the query as one single prompt to an LLM. You can think that it is GPT-4, for example. And GPT-4, together with the query and the relevant documents, will come up with an answer which is grounded into facts, hopefully. And it will be sent back to the user. So how does this look like in code? As my man Omar would say, a man gotta have a code. So first we'll configure our Llama index pipeline. So we have to set an embedding dimension. So an embedding dimension is essentially a configuration of the embedding model, and we are telling it how many numbers to store in each vector. So this configuration controls how much information is being sent, and you can think about how if you make it too big, it will probably cost more and maybe be inefficient. And if you make it too small, then it might perform not as good as you hope for. Then you're going to load the environment variables, just for getting all of the secrets for interacting with the OpenAI API, and set the embedding model that you're going to use. After that, we're going to read in all of the documents. So Llama Index provides this nice class called Simple Directory Reader. And all you have to do is give it a directory path and the formats of files that you're going to use, and it will just read through all of them automatically. You don't have to do anything else other than that. Once you've done that, you can do some text cleaning. So you can basically customize it to whatever you want, depending on your own database of documents. But in our case, what I decided to do is replace tabs with spaces and replace paragraph separators with spaces as well. These tabs and line jumps, sometimes they can throw off the LLM when they are fed into the LLM. So this is something that you want to take into account. After that, we're going to create the actual vector store. So once we've read in the documents, we've embedded them, we've stored them in there. Now we want to store them in our vector database. We want to split them because when we eventually want to search for all of the documents, the size does matter. If the chunks are too big, then you might get information that you don't need, or you might not find the information that you need. If they're too small, again, the same problem. You might not find the information that you need in your query. So you see how with very few lines, we've created a vector store of our documents, and then we submit a query with simple human language. What is the S&P's policy on climate change? Then we use the query engine to query with that human language query, and we already get really good results back. So these results, maybe you don't know the S&P's policy on climate change, but I've read it, and I can tell you this is pretty good already. But what are the limitations of the standard RAG? So sometimes, and this is maybe one of the biggest problems, the results that you get from the actual similarity search when you're querying through your vector database are inaccurate or irrelevant. So you might actually be missing the critical information that you are looking for in your database. Other issues are domain adaptability. So if you've built your RAG with one domain in mind, for example, in the medical world, if you try to use that same model for a different domain, just by hooking it up to more text, it might not work the way you expected it to. And finally, when you eventually deploy this to production, you have to think about scalability. So as the number of documents increase, the retrieval time also increases because it has to search through more documents. And also, and this you might have seen already if you've tried to play with these tools and you've played around with OpenAI API, there are rate limits because people from all over the world are querying these LLMs at the same time. You will hit rate limits depending on your subscription level. So that is something you need to keep in mind. But how can we improve our RAG? There are multiple ways to do this, and this is a growing field. So I'm going to show only a few methods that I thought are really useful. But this is a live kind of like discipline that is growing, and the community is also coming up with more methods all the time. So the first one is called hypothetical document embedding, or in short, HYDE. So HYDE aims to solve the problem of not retrieving the documents that you want the query to retrieve. And how does it do that? Given the user's query, it will create a hypothetical document using an LLM, meaning we will take the query, feed it to the LLM with an instruction of creating a hypothetical document. And then that hypothetical document will be embedded to then be searched for documents that look like it in our vector database. So in architecture, it looks like this. A user generates a query, then the LLM application will send a hypothetical document that was generated by GPT-4 to an embedding model. And the embedding model will return the embedded hypothetical document back to the LLM application. And then we will search for documents that look like that document in our database. Then together with that, with those documents, again, as before, we will send the grounded answer back to the user. So in code, Llama Index makes it really easy to create this. They also have a built-in hide retriever, but I've shown you how you can build it from scratch, just so we can see how it looks like. So we're going to use the OpenAI GPT-4o model, and this configuration argument here is very important. So temperature essentially controls the creativity of the LLM. If you set it to 0, what you're telling the LLM is to be very confident of its answers when it replies back. It doesn't mean it won't hallucinate, as we've seen with models all over the internet, but it is less likely. If you set it to 1 on the other extreme, it will be very creative and it might create a lot of hallucinations. So the rest of the arguments are pretty self-explanatory. And this is the prompting configuration. So we are embedding the query into a prompt, and we are telling the LLM to generate a hypothetical document that directly answers this question. And the document should be detailed and in depth, and the size, and this is very important, the size has to be exactly this size. And the reason is because we want the generated document to be similar in size to the documents that we already have in our database. Then this is fed into a query pipeline, which will be later on served to the LLM. And yeah, we basically set it up as a retriever, so we can look at the retrieved documents in this example. So just to look at an example in our use case, we've set it up. And this is the generated hypothetical document. We're not going to read it. Again, it's very long, but you can take my word for it that the retrieved documents are actually very similar to the document that was generated by the LLM. But this could go wrong. And can anyone guess how it could go wrong? So LLMs have been trained on data that is available in the internet, right? So they scrape, like the companies that create these models, they basically scrape the internet for all of the textual data that they can find. And when you are asking the LLM to generate a document based on a query, it can actually look at the data that it was trained on and come up with a document that is already publicly available. Now, given that you want to build an LLM for an internal document database, which is not publicly available, this might bias your model, and you might not find the actual documents that you're looking for. So that is something to keep in mind with this method. Next method is called query transformations. So again, this is for solving the retrieval of the most relevant documents. We're going to look at 3 of them, but you can think of many, many, many more. First one is called query rewriting. And again, we're going to use the Llama Index prompt template, which is very useful for the same query of what is the S&P's policy on climate change. We are instructing it to reformulate the user query to improve retrieval in a RAG system. So given the original query, we want to rewrite it to be more specific, detailed, and likely to retrieve relevant information. So configuration looks similar to what we've done before. Then this will generate the query for us. And if we look at this original query of what is the S&P's policy on climate change, you can see it's really short. There's not a lot in it. When we look at the generated query that was generated by the LLM, we can see it's much broader. There's more information in it. And maybe, we don't know, it requires testing, it will come up with more relevant documents when you actually do the search. Step back prompting. So given a user's query, we want to create broader, more general queries to improve context retrieval in a RAG system. So given some kind of specific question, we want to take it a step back in a higher resolution and to ask a more general question. How does this look like? So for a more specific question, what is the S&P's policy on carbon emissions? We will get a generated query, which is what are the general policies and positions of the S&P on environmental issues? Again, maybe this will help us with retrieving the most relevant documents. I personally think from personal experimenting that it does, but again, it does require testing in your use case. And finally, we have subquery decomposition. So with subquery decomposition, what we are doing is that we are breaking down complex queries into simpler subqueries. And you can imagine how in previous queries, it was a sentence long. It was very short. But sometimes some users might come up with very long queries. It just depends on how they're using your application. And when these queries are really long, you can think that maybe there are multiple topics in the same query. Maybe the answers to these questions, they come from different documents. So that's why you want to decompose it into multiple different queries. And actually, with this prompt here, we're doing something that I haven't shown up until now, and that is called one-shot learning. So not only we're giving the LLM an instruction, we're also giving it an example of how a real answer should look like. And this is sometimes can be very helpful with these kinds of prompts. So for an original query, what is the Conservative Party stance on immigration? We get generated subqueries that are more specific questions based on this original query. Next method we're going to talk about is called contextual chunk headers. So you can imagine that if you split your documents into small chunks, sometimes the context of what are we even talking about is lost in the process. So let's say you have a very long document about the S&P's policies on multiple things, and then you split it in a way that you have a sentence saying, we want to reduce carbon emissions. But what are we even talking about is lost in this process. So what we do with contextual chunk headers is that we're adding some kind of like metadata information about that specific chunk in the actual text, and then it will embed that information together with the text itself. Okay, so I will breeze through the code just because I don't have a lot of time left, but this is how it looks like. Just a word of warning, sometimes it performs better with the headers and sometimes not, so proceed with caution is my advice. I don't have time to go through semantic chunking, but I do recommend you look into it because it's a very powerful tool. Okay, I do want to leave time for questions. So what have we covered? We talked about RAGs and what are they good for. We've talked about limitations of RAG systems and how it can sometimes be challenging. And then finally, I've shown a few methods on how you can improve your RAG system. There are other ways to improve RAG that I haven't talked about, but you should consider them if you want to deploy this kind of tool to production. So evaluation is very important, fine-tuning, prompt engineering, and so on and so on. I highly recommend, if you are looking to learn more about this, also visit this repository. It has many, many different methods on improving RAGs, and I've gained inspiration from it, definitely. Okay, that is it. Thank you very much for listening and attending. I will take questions.
When you're using metadata for retrieval from something like Chroma, we've done a lot of it, and we found sometimes it can favor the metadata over the actual context or the encoding. And what we're struggling with is two documents may seem very, very similar, 99% similar, but what distinguishes them is a nuance that's only known by expert users. So do you have any recommendations on how you encode those nuances to distinguish the documents?
No, because I haven't ran into the same problem yet, so I don't know how to solve it. But I do recommend when doing the evaluation. So I don't know what tool you're using for that, but there are tools like DeepEval and LangSmith, which are very good for evaluation. So use your domain experts to write the test cases. And when you are using the domain experts for writing the test cases, then you can be confident that you're pinpointing the actual behavior that you want the LLM to behave. Yeah.
So when you mentioned hypothetical document embedding, you mentioned that the generated hypothetical document has to match the chunk size. Could you generate something that's a multiple of that chunk size and then chunk it, and then match on the different chunks? Have you tried anything like that? And is there potential performance improvements there by doing that?
That's a good idea. I have never thought about it, but that is definitely something that you can do. It's a good idea.
So I imagine when you're using GPT-4o, when using hide, I imagine it's going to kind of add more cost to the retrieval when you're generating that API. So what's your recommendation there as a mix of the improvement methods? And also, have you tried using the open weights model for the hide method?
Yeah, that is true. Cost is definitely a consideration. So if you're on a low budget, then you can think about things like hosting your own models, training your own models. But also something that we found very powerful is caching. So if you cache the answers, the hypothetical documents that you generate, that saves a lot of cost. So maybe that would be the first thing that I would try.
You mentioned dropping the temperature right down to 0, and I know I've seen some articles lately talking about how it's really a choice between the results from the LLM. Have you tested, I'm not challenging you for a second,
yeah.
I'm just wondering, have you tested the effectiveness of that versus 0.3 or versus higher?
So the effectiveness of setting it to 0 versus choosing between different answers?
Well, does it truly make it better?
Oh, yes, 100%. We have seen some really creative answers when we've tried anything different than 0. We've also seen that it's not entirely set to the facts. It can still lie if you set it to 0. So you have to be cautious with it. You can say in the prompt, write something like, only answer with facts from the document served for you. And that will make it even more grounded into truth and more confident of its answer.